Clouds play a crucial role in moderating the Earth's energy balance. They cover more than 2/3 of the planet's surface, and they reflect nearly a quarter of the incoming solar radiation back to space. So small changes in clouds can lead to large climatic effects. Arguably, the study of clouds began with their first kind of scientific classification by Luke Howard in 1803. And that original classification has since evolved into the 10 different types which the World Meteorological Office, the WMO, now recognise as the classifications such as cumulonimbus and cirrus and stratus, which many of us are familiar with today. And these classifications are very valuable for being able to quantify and determine the changes in clouds due to global warming, and for example, stratifying the effects of aerosol on these different types of clouds, whether the processes act in quite different ways. But measuring these types and classifying them from space remains very challenging because some of these definitions rely on measurements of their depth, for example, which passive instruments from space can't accurately determine. Fortunately, the NASA A-Train, which is a constellation of satellites, includes a number of extremely valuable sensors, both active and passive. So there's the Calliope LiDAR aboard the Calypso satellite, combined with the cloud profiling radar aboard CloudSat, provide a very detailed and accurate classification of clouds using these active sensors, but only over a very narrow region, over a very narrow swath of a few kilometers. So they're only able to classify these clouds globally once every 16 days or so. But another important instrument in the A-Train is the multispectral imager MODIS aboard Aqua. Now, that provides 1 kilometer imagery for the whole globe every day. Now, Cumulo takes the high fidelity data from CloudSat and Calliope and trains an algorithm to make the same classifications but based on the MODIS multispectral data, providing global daily classifications of these high fidelity cloud types. We use an invertible ResNet to learn a latent representation of these different cloud types from the MODIS imagery, based on both the unlabeled parts of the MODIS image and the very narrow region of labels which we have available from CloudSat and Calliope. And this embedding, this latent representation which we learn, has added benefits in that it allows us to predict subclasses which we didn't necessarily have labels for. So while the labels provide a broad classification, we can dig further into that to determine possibly new types of clouds within this representation. So we use 1 year of data, or around 100,000 of these 1 megapixel MODIS images, combined with these CloudSat and Calliope labels to provide the training data set for this algorithm. But we evaluate it not only on those sparse labels that we have, but also on the physical properties of the clouds, such as their liquid water content and their optical depth. And these high resolution classifications really help us explore and monitor the effects of anthropogenic pollution on clouds, and in turn the effects of those changes on the climate. And these climate feedbacks due to clouds are among some of the most uncertain and important questions still being asked in atmospheric physics, and Cumulo provides a really valuable tool in being able to answer some of those questions. In the future, we're looking to extend Cumulo to include, for example, phase information from Calliope, so the ratio of liquid to ice water in these clouds, which is another valuable quantity to know about from the climate point of view, but also potentially precipitation, so being able to determine the low amount of precipitable water, again from MODIS, would give us an increased understanding of the processes going on in these clouds at a global scale. But there are also opportunities for the machine learning community. So this is a weekly supervised data set. It's very large. There are multiple labels, so some pixels can be labeled for multiple classes because they may be layered. And there are large class imbalances, so clouds like stratocumulus can occur much more frequently than cumulostratus, for example, and so these provide challenges for these machine learning data sets. And we hope that by opening up the data set as well as this algorithm, it will encourage some of the ML community to engage with these important questions.